Hey, good morning, everyone. I just finished up reading the last homework, I think chapter 7. And one of the questions you all got wrong. I mean, most of you. Some students did okay. It seems that you all copy from the same source. Are you guys copying things without thinking? What is the source of the error? The source of the error is this: you have a conducting sphere that has a charge outside. So you all got right. The electric field inside the shell should be zero. Therefore, all the charge is outside. There is no charge enclosed. And then you can say that if you take a Gaussian surface inside the sphere, right, at a radius r, then when you apply Gauss law to it, total flux of EdA is equal charge enclosed divided by epsilon r. But since this sphere supposedly is in electrostatic equilibrium, then the electric field inside is zero. Therefore, the charge enclosed must be equal to zero, which means all these 5 coulombs should be outside, right? So that's the first step in solving the problem. So let's use the fact that electric field is zero inside this sphere, and you don't have charge in there. So to calculate the voltage, that is the first question. So how do we do that? So you use the expression dV dr is equal negative of the electric field of gradient of, or if you want a more complex, the gradient of your voltage is equal the negative of your electric field, or you use this simpler expression here. So dV dr is equal negative E. So dV is equal negative E dr. And then you integrate that. You integrate from where? So you're going to add all these contributions from the center of the sphere, 0, all the way to the radius of the sphere, r, right? 0 or a. And then we find in the left-hand side, VA minus V at the center is equal to negative the electric field, which is 0. So it's pretty much 0. So the only conclusion you can make is that V at the surface, at the point A right here, is equal to the V inside the sphere. In other words, the voltage is constant. The voltage is constant inside the sphere. That's the only thing we can conclude. So V is a constant. You don't have any other information here. So when you go to the part outside the sphere itself, so you have 5 microcoulombs. So before you hit the shell, right? So somewhere here. So when you apply Gauss law to that position, you find, and I'm not going to do it because you guys, I did in class, the electric field outside is the same as if the entire 5 coulomb charge were concentrated in the center, K times the charge Q, which is 5, divided by that distance square. So you have the electric field. So what do we do next? We repeat the same thing, right? dV is equal negative E dr, integrate, and we are integrating now from position A to position R. So the left-hand side of the equation, we get VR minus VA is equal negative of, and then you do the integral of KQ over R squared from from R to A, this is going to be equal to negative of k q over R from R. No, I'm sorry, this is not correct. It's from A to R, right? We are integrated from A to R, from A to R, right? And then VR minus VA, and from A. So this is pretty much from A to R. We are getting out of the sphere surface and going to the point R. So basically VR minus VA, which we don't know, is equal to plus KQ 1 over R minus 1 over A. Okay. And then what? So we can't, we know A, but that is the expression for the electric field. So it seems, for the voltage, I mean. So it seems that the voltage, so let me just do one thing here. So A is a number less. So this is going to be a negative value. So VR should be less than VA, basically. So the voltage is diminishing, going outside from this positive point, right? VR is less than VA, and then let's keep on moving. So let's go to the shell. So we did the sphere. Now in the shell, when you do your Gaussian laws for the shell, we find the electric field area is 0, right? Therefore, the charge in the inner shell must be negative 5 coulombs, which makes the outside surface to have a charge of plus 5 coulombs. Then to find the voltage inside the shell, same equation, dV dr is equal negative of the electric field, which we know is 0. So we find the voltage by the same token. The voltage inside shell must be constant, and which means the voltage here, the voltage in the inner shell is what? Well, we found that VR, VB, which is this side here, VB minus VA is equal KQ 1 over B minus 1 over A, right? So then we can find that VB is equal to VA plus KQ over 1B minus 1 over A. So again, so VB is being determined as a function of VA, which we don't know what it is because we haven't found yet. And VB is the same all through the shell and is the same here, right? This is VB right there. Now we go outside the shell. Shell is right here, so we go to a point R right there, right? And you know what we're gonna do? dV is equal minus, and the electric field is of the following expression. and we are integrating from B to R to find the electric field in R, from B to R, and then VR minus VB is equal, that's going to be KQ 1 over R minus 1 over B, and then we can find our VR as a function of VB, and then our last step is using the information given in the enunciate, and that is, if R becomes too big, the voltage is 0. Then 0 should be equal to VB plus KQ, and then R is a big number, right? So this becomes 0, negative 1 over B. Therefore, VB is equal KQ over B. So we found VB, right? So we have VB, which is V is here, which is the same there. We plug it in here, then we find our VA, and then we find the voltage inside the sphere. So let me know if this makes sense to you.